Hi, my name is Chung Jui Yu, and I'm a fourth-year chemistry graduate student in the lab of Professor Dana Friedman at Northwestern University. One major effort in our group is the design of molecules and materials for quantum computation. Developing a quantum computer can usher in new capabilities not achievable with conventional computers, such as simulating the way proteins fold. Now, let's learn why quantum computers are so much more powerful than our normal everyday computers. Our everyday computers use bits that exist in either the 0 or 1 state, as shown here with the 0 in blue and the 1 in red. Quantum computers, on the other hand, use quantum bits or qubits. These qubits exist not only in the 0 or 1 state, but also as any combination of those two, which is known as the superposition state, as shown here in the spectrum of purple. It is this superposition state that gives quantum computers their extraordinary capabilities. The big question is, what can we use as our qubit? One of the core concepts that we use in designing our molecules is the idea of crystal field theory. Depending on the d orbital's orientation relative to those ligands, some will feel more repulsive forces than others, leading to d orbitals of different energies. So, by changing the arrangement of ligands surrounding our d orbitals, we can actually tune the electronic structure of our molecules and the orbital that our electronic qubit is housed in. In my research, I apply crystal field theory in designing my molecular qubits. In one of my projects, I synthesized a vanadial complex with square pyramidal geometry, shown here on the left, and compared it to a trigonal prismatic vanadium complex, shown here on the right. I wanted to see how this change in geometry changes their electronic structure and their performance as a qubit. To measure their performances as qubits, we use a technique called pulse electron paramagnetic resonance spectroscopy, wherein we use microwave radiation to excite our electrons. Using this technique, we found that the vanadial complexes showed a 10 times improvement in qubit performance relative to the vanadium complexes. This shows that even a small change in geometry can have a massive impact on their performances as qubits. Researchers throughout the world have been captivated by the idea of quantum computation and the promise that this technology provides. However, to realize this promise, we need to understand how to design and tailor molecules and materials as qubits. The work that we do in the Friedman group shows that by using principles as simple as crystal field theory, we can uncover principles governing the design of qubits.